What's going on, everybody? It's day, I don't even know, 122 of not being able to get a haircut because of you know what. So we're just going to put a hat on this for now and forget about it. But yeah, today we're going to be talking about U-substitutions. And with U-substitutions, we are trying to make a integral that we can't use reverse power rule or use our integral table on. We're trying to make that integral nicer into something that we can use reverse power rule on, or our integral table. Okay, and so that's what we're going to be talking about in this video. So at the start of this video, I'm just going to be giving you an introduction. And in this introduction, I want to talk about how with power rule, right, we have a reverse power rule for integration, right? But what about the reverse for the other derivative rules like chain rule, quotient rule, product rule, all that? And so I'll talk about where U-substitutions fits into that entire picture. We'll then talk about U-subs just with what they are, like what the notation is, all that stuff. I want you to be comfortable with that before we hop into the loads of practice that I've packed into this video. So we're going to do first U-substitutions with indefinite integrals, and we'll do some practice there. Right, so integrals that don't have those numbers on them, integrals that you're not using the fundamental theorem of calculus on. And then we're going to get into U-substitutions with definite integrals, right? These are integrals where we do have those bounds, right? We're plugging them in at the end. We're doing all that. It's like indefinite integrals, but it's like one step further, okay? And then we'll do some practice there. And then we're going to work on some weirder U-substitutions. You could also call them, I guess, harder U-substitutions would be good. These are definitely going to be the integrals that I struggled with more when I was going through this. Just some of these substitutions really didn't make much sense to me at first. And so I really want to save that to the end, kind of build up to them. And then at the end, we'll go through that. We'll talk about those different integrals and why I struggle with them and how you can, not struggle with them. So then we'll do some practice with that, and yeah. And of course, as always, I do have the unfinished and the finished notes linked as PDFs in the description down below. Now, before we get into this video, I quickly wanted to mention my full Calc 1 course, which I'm going to have linked in the description down below. Like I just mentioned, I've been through Calc 1. I've been there, done that. And so I get the whole feeling of, kind of learning the stuff in class, trying the homework, and then your mind is just like a garbage truck, and then it just dumps everything that you learned and you forget about it within a week. Now, I don't want that to happen to you because it makes studying for tests, and you probably have finals right around the corner. So especially finals, it makes studying for that stuff way more stressful. You're starting from square one. And that's why in my full Calc 1 course, I have a bunch more practice problems for you to try. And I also have video explanations for every single problem in the course, so you don't have to sit there scratching your head, wasting your time. So if you're interested in that, be sure to check out the link in the description down below. Now let's get into this video. So I want to start with the introduction, and this introduction is going to be short and sweet. I just want to talk about the different rules that we have for derivatives versus, where that's going for integrals. For derivatives, we have, first off, power rule. Right? And with integrals in the last couple of videos, I've been talking about reverse power rule. And that, of course, was the idea of saying, well, if we want to take a derivative of x squared, right, that's going to give us 2x. But if we want to integrate 2x and get back to that x squared, we're going to take this power, which is a 1 here, right? And we're going to raise it by 1, giving us x squared. And then we bring that power out front and we flip it, giving us 1/2. Now, of course, there was a 2 there, so I'll make a little room, put that in there. And you see the 2's are going to cancel. And you're left with that x squared. But that was the idea with reverse power rule, right? We were just reversing this process. And of course, there's going to be a plus c on the end, but this was just back of the envelope stuff. So, anywho, what's the reverse of chain rule? And what about product rule and quotient rule? Well, that's a valid question. The reverse of chain rule is basically what we're about to do in this video. That is U-substitutions. That's where that fits into this entire picture. Okay, integration by substitution is, I guess, the long form of saying that, but usually you use the variable u, and so people say u-substitutions or just u-subs. Now, product rule and quotient rule, they're actually the same process, really. I mean, they're not very different from each other. Let me try to make a cool arrow here. See if I can do it. Oh, all right, I'm going to go with that. This is integration by parts, and you haven't learned that yet. That's more of a Calc 2 thing, but you might learn it in Calc 1, just towards the end. But yeah, product rule and quotient rule are kind of the same process in the way that, you know, if you're trying to take a derivative of like something like cosine of x over x, you can use quotient rule here to do this derivative, but you could also write the x in the numerator, right? And just write this as like x to the negative 1, right? Because this is a 1 over x right here. If you just think about everything else but the cosine x, right? This is a x to the negative 1. And so that's being multiplied by cosine of x. And so you can use product rule for the same problem you would have used quotient rule for. And so that's why it should kind of make sense to you that these two end up being the same process in reverse, or the same process for the reverse. But yeah, that's what I would say there. But yeah, in this video, we are going to be talking about u-substitutions. It's essentially reverse chain rule. So let's get into this whole u-sub idea. And to be honest, I feel like how u-subs are taught a lot of the time is, you know, just kind of like they were like chain rules usually taught. With chain rule, I'll show you exactly what happens. A lot of professors or a lot of teachers will start with just saying, hey, here's what chain rule is. And you're like, what is this? Right? And I'm sure you probably remember that feeling. Now, reverse power rule, or not reverse power rule, u-subs is kind of the same idea. You get shown something like this and you're like, oh yeah, we're just gonna let u equal some things, and then oh look, it works. But I want to show you a little more in depth how a u-substitution works and how it actually reverses chain rule. Okay, so let me give you a better picture of what's going on. And then we'll introduce some notation. So first, I'm going to take the derivative of this guy. This guy requires chain rule for me to take that derivative. And so the derivative of this guy, right? We have that d over dx to signify that we want to take a derivative. It's going to be, we'll use a bracket. We'll do x squared plus 1 cubed. Cool. And so we're going to pull that 3 out front, just like it's power rule, and we're going to leave the inside alone. And then we're going to replace with a 2. And then we multiply by the derivative of the inside. That's what chain rule says, right? We leave the inside alone to start off with, and we take a derivative like normal. We use, you know, power rule like normal. And then we take that derivative of the inside as kind of like a consequence of the whole thing. And so this becomes 6x times x squared plus 1 squared. And that's chain rule. So the question is now, how can we reverse this process and get from 6x times x squared plus 1 squared back to x squared plus 1 cubed? So we're going to talk about that. First, I want to show you the notation form of what we just did, because I'm about to get into the notation for a u-substitution. Okay? So we started out with a kind of like a function inside of another function, right? We have this where we would usually see something like a x cubed. Okay, now we have an x squared plus 1 cubed. And so that's how you can think of this, or if it'll be easier to spot if you instead write this as like a u cubed or something. You can see how, you know, this would be a function. This would be kind of the outer function. But this u is another function in and of itself. It's an x squared plus 1. And so that's where you get the idea of a function inside of another function. And so what ends up happening is you take the derivative of that outer piece, leaving the inside alone. That's what we did with the u cubed, right? We made that a 3u squared. That was, you know, again, just setting x squared plus 1 equal to u here. And then we took a derivative of the inside. And that was, again, we call the inside u. Take that derivative, you're going to get 2x. Right? And so that's what the chain rule says. Take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. Okay? And if you can understand that, and you understand me plugging in u in different places just to help you understand the idea of a function inside of another function, well, what I actually just did there was I made a u-substitution. We're now going to do that to help us simplify integrals. Because as you might be able to see here, with this integral, we're not going to be able to just use reverse power rule. I mean, we could if we distributed this out with, that square and all that, and we multiplied it on the 6x, but that takes too long, right? Or at least it will if you have something like a cube or a 4 or a 5 or whatever. And so that's where u-substitutions come in. And so, like I said, the idea is to turn this into a simple integral. We're going to do that now. So remember that this was the chain rule notation. And so how do we reverse this thing? Well, what we're going to do is set up this integral. And we're going to do exactly what I was just talking about. We're going to set this inside function, that was x squared plus 1 before, we're going to set it equal to a u. We're going to say u equals g of x. Okay? What that does for us, watch what happens. It makes things a little nicer to look at. We get f prime of, this is where the u will go, and then we'll have g prime of x dx. Right? But that's not the only substitution that I want to make here, because we still have, this looks a lot nicer, this piece, right? We've simplified that down to just be, kind of a single variable there, not an entire function. But what about this guy, right? If we've replaced g of x, we should replace g prime of x. And we can do that. All we have to do is take a derivative, right? Like we did. In chain rule, we take a derivative of the inside. That's what we do when we do a u-substitution. We're going to do du over dx. That's what the derivative of u would be. And that's going to be equal to g prime of x. And then how we use that for a substitution is we multiply the dx over. And so that's why in a u-substitution, you'll see people write it as du equals g prime of x dx. And so with this substitution, now this guy is going to become du. And this has simplified the integral a lot. Right? Now, we just have something that looks a lot nicer. Okay? I know it's kind of weird to make that connection with notation. You're like, well, how do I know it looks nicer? I get that, right? I get where you're coming from. You'll be able to see that a lot more when I actually start plugging in numbers. But just know that what we've done here is we've now turned this integrand, that's the thing that we're taking an integral of, we've turned this guy into something that looks a little nicer. And so we can take that integral a lot easier. So let me show you this with the actual example that we were supposed to do. So the actual example that we were supposed to do was the integral of 6x times x squared plus 1 squared dx. And remember, if we were going to get this thing right, we should end up back at an x squared plus 1 cubed. Of course, there's going to be a plus c on the end, but that's what we're going to end up with. So let's see if we get that. Well, how do we make that u-substitution? Well, it's equal to that inside function, right? And the inside function here is that x squared plus 1. You can just tell that, right? Like, let's say you didn't even take that derivative in the first place to get to this point. Well, this guy is inside that square, right? And once you get good at these, you might be able to see that when you take that derivative, and I'll just write du for now and assume that you understand that you multiply the dx over to the other side. Once you get good at these, you'll be able to see that, oh, if I make this my u, then this guy's going to go away. du here is the derivative of x squared plus 1, that's 2x. And then we add that dx on the end that I mentioned earlier. So that's nice. We can plug this in here, but you got to be careful because look at, here I have a 6x dx, here I have a 2x dx. And so how I can actually end up replacing this is if I keep a 3 here, right? I could write this as like 3 times 2x, right? And then that 2x is going to go here, but the 3 is going to stay. So hopefully you can see that, right? And so this ends up being 3 times something squared. That's going to be the x squared plus 1, which we are now calling u. And then this 2x, the two that we're taking from the 6, the x and the dx are going to become du. Okay? And so now this integral is a lot nicer, right? We have the integral of 3u squared du. And we can use reverse power rule on that. You see what I'm talking about now with this thing becoming simpler? Right? Now we can do this. I'm going to just make this a little nicer quick. I apologize for erasing things, but I'm going to take that 3 out just so you can see the whole reverse power rule process a little easier. If we use reverse power rule on this guy, we're going to get 3 times, it's going to be a u cubed, right? We just raise the power by 1, and then we're going to bring this guy up front and flip it. So instead of 3 over 1, it's going to be a 1 over 3. And then, of course, we need to add on our c at the end. So we get a 3 times 1/3, that's going to become 1. And so this is equal to a u cubed plus c. Now, here's a mistake that people make, so listen closely. People leave this as u cubed plus c, and they'll say, that's my answer. No, it's not, okay? Because what was the variables in our original integral? They were x's, right? And so you need to have your answer in x's. It just like makes sense, right? I mean, you don't want to just, say, here's what it is, but I'm going to use a completely different variable. It's fine. You're good. No. Okay? So we know that u is x squared plus 1. This gets cubed. Then you add c. That's your answer. Was that what we were expecting? Did we get back to where we wanted to be? Yes. And so again, we said that u equal to the inside function, just like I was talking about with the notation, and the du gets rid of that derivative piece on the outside. Right? The du got rid of that 2x for us, which we could take out of the 6x there. Right? And so now we get something completely in terms of u. It's nicer. We use reverse power rule. And yeah. So let's keep doing some examples with that. We'll keep going here. And now I can get a little bit quicker with this type of stuff. Okay. Here we have the integral of 2x times the square root of 1 plus x squared dx. And with this, what do you think our u-substitution is going to be? Well, what would you call the inside function here? Well, it would be that 1 plus x squared, right? That 1 plus x squared is being trapped. It's definitely looking like the inside function. And you might also be able to see that if we take a derivative of this guy, then we're going to get 2x, right? That's what's on the outside. We're going to get that dx2, and that's going to go away. So you just start to see these things in your head as you get good with them. And so you don't need to see them yet. It's fine. Like, I get that it takes a while. I'm just trying to help you see that and make those connections in advance. So again, we set the u equal to that inside function. And the derivative, du over dx, multiply the dx over, that's why it's over here now. The derivative of this guy is 2x. And now you can make those substitutions. You get the integral of, this is going to be the square root of, instead of 1 plus x squared, it's now u. And then we have the 2x dx, that becomes du. And so, to take this integral, it's the integral of u to the 1/2 du, right? That's what a square root is. It's 1/2, right? And so reverse power rule again. This guy is going to get raised by 1 to become u to the 3/2. And then we bring it out front and flip it. And so instead of being a 3 over 2, it's now a 2 over 3. and we add on our c. And now we're just going to plug in for u. U is 1 plus x squared. So you see how quick that is, right? When you have a u substitution like that, and you notice what the inside function is right away, you see that substitution, the problems are pretty quick at that point, right? If you can see the substitution, you can see what's going to happen. You have that kind of, I guess, foresight. Yeah, these problems are going to be really easy for you. So anyways, let's do some practice with this. Let's do some more. We'll do now a practice with an exponential. And so here we have the integral of e to the 5x dx. And for this integral, what would you say is that inside piece? Well, yeah, here it's a little bit different, right? With before we had like, two pieces. We had the piece that was obviously on the inside, and then the piece that would cancel when we use the derivative. Here it's not so obvious. Yeah, you might think that the 5x is on the inside, and so yes, that is going to be our u here. But then what would the du be? What is it going to cancel with? Well, remember, this is 5x, and so when we take a derivative, it's actually just going to give us 5. And remember, of course, we now have a dx here. So we don't need anything to cancel. We just need the dx. We can divide away the 5 and create our substitution. Since we don't have a 5 there in the integral, we're just going to write 1 over 5 du is equal to dx and use that as our substitution. So where we see this dx, we stick this guy. So this integral becomes the integral of e to the u now. And then we have times a 1 over 5 du. And so we write this as 1/5 the integral of e to the u du. The integral of e to the u is e to the u. And so this is 1 over 5 e to the u plus c. And u is 5x. So there you go. You have your answer. 1 over 5 e to the 5x plus c. All right, awesome. Man, it is getting hot in my room. All right. Next we have the integral of cosine of pi x over 2. This is the exact same thing as the last example we had. And I promise these examples are going to get harder. I just really want you to get comfortable with this at first. If you're comfortable with this, you're going to get comfortable with the more difficult stuff down the line. Okay? And really, it doesn't get too much harder than the stuff that you're doing right now. Okay? Really, it's going to be, you just got to see a couple more things going on before you actually make your substitution. That's as hard as it's going to get. And you'll see that as we move on. But here, yeah, you can see that the inside of the cosine is not x, right? So we're going to make that our u. Okay, don't let the whole pi also being in the numerator with the x freak you out. I think that probably freaked me out a lot when I was in calc for some reason. This is just a pi over 2 times x. Same thing. I just wrote it a different way. And there you might be able to see that it's a little easier to see the derivative. So du is going to be pi over 2 dx. Now, we don't have a pi over 2 dx in our integrand. We have a dx, and that's it. So we're going to divide by pi over 2 on both sides. And to do that, we're just going to flip the pi over 2 and put it up. So this is going to be a 2 over pi du is equal to dx. And so this is our substitution. Where we see the dx in the integral, we're going to put a 2 over pi du. And so this becomes the integral of cosine of u times 2 over pi du. And this is going to become 2 over pi, the integral of cosine of u du. Just pull that 2 over pi out. We don't care about it. It does not matter to us at all. Integral of cosine is sine because the derivative of sine is cosine. So you just do the opposite, right? And this guy becomes 2 over pi times the sine of u, add on your c, and you're Gucci. What am I even saying? All right, so then you're just going to put in pi over 2x for u. And that's it. That's really it. That's the problem. And so now, if you feel comfortable with this, really, again, definite integration, that's the topic we're about to move on to. It's not going to be that much harder. It's just a little bit of a different process. Like there's like one thing that's different. And you also, with definite integration, you won't need to make this substitution at the end. And we'll talk about that in a second. It's to not make that substitution at the end. You might not think anything of it right now. Like this isn't that bad. But when you get into some Calc 2 stuff, it's going to be so disgusting to try to plug that back in at the end when you start dealing with like trig integrals and don't take me back. Anyways, here we have a u-substitution problem, but now we're dealing with a definite integral. And so how does that change? Well, let's just do everything like we normally would. We're going to make our u 2x plus 1. It's inside that radical. And so, yeah, let's just do that. Notice that you can't just evaluate this normally with the reverse power rule. You're going to have to use a u-substitution, right? So that's why we look to u-substitution. So it's not like the first thing you should think of in your head. You should think, can I evaluate this nicely at first? But the derivative of 2x plus 1 is just going to be 2. And then we tack on that dx on the other end. And since we only have a dx and not a 2dx, we're going to divide that 2 away to get our substitution for dx. Okay? So, here's the thing. We now get the integral of the square root of u times, instead of a dx, we now have a du over 2. The problem is, and the thing that people forget, is that our bounds were with respect to x. Okay? You got to realize what's going on when we make a u-substitution, right? You end up integrating two, they're the same value, but you're transforming a function. When you take something like x squared plus 1 cubed, that function looks a lot different than something like u cubed, right? If you just make that x squared plus 1 a u, those two graphs look different. And so the whole area you're finding and all that, you know how a definite integral is the area under a curve? Like let me just show you what I'm talking about here. If we have something like this, I'm just drawing two random curves here. With a u-substitution, maybe we're making it look like, I don't know, like this, right? Let's say that it just ends up being that way. And for a definite integral, you're trying to find the area under a specific portion of the curve. So let's say it's from 2 to 5 in this case. Okay, and like this one is with respect to x. So here's the area, right? Well, on this new graph, that area doesn't have to be between 2 and 5, right? That's not going to be the equal area. You could even see that, right? I mean, like let's just mark out 2 and 5 here. You see how this area looks a lot different than this area? So what I'm saying is the bounds have to change to be with respect to your new variable, because you're dealing with a different graph now. You can't just keep the same bounds as you had before. So maybe in this case, maybe the 2 stays and then the 5 becomes a 3. And then you have two areas that maybe start to look a little more equal here. Of course, when you make a substitution, you're saying that, oh, this area is equal to this area. And so that's why we can make that substitution, because when we, evaluate when we're trying to integrate something like this, it ends up being the same thing as if we just plugged in a u and did some magic and all that. Okay? So that's kind of the conceptual stuff, but to be honest, to put this into practice is really, really easy. You're going to be blown away at how easy this whole thing is. So we take our first bound, that's x equals 0, right? That's like, the first guy we're integrating from. And we're just going to see what this is in terms of u. What is x equals 0 in the eyes of u? Well, just look at our u conversion here. Plug in. U is 2 times 0 plus 1. So that u is going to be 1 when x is 0. So the lower bound here is going to be 1. Right, it replaces the 0. And then we have x equals 4. What is u going to equal? Well, we plug that into our u equation, and we get that u is going to be 9. And so our upper bound is 9. And so now we can just go and we can actually integrate this thing here. It's going to be pretty quick from here. All you have to do is just a little extra work during that substitution phase. Okay? And you got to remember to do that. That's going to be something that, probably 75% of you forget. But I'm telling you now, don't forget it. So, yeah, we're going to pull this 1/2 out that's going to be in here. And then we get the integral from 1 to 9 of, we'll make this rad u a u to the 1/2 du. And so now from here, this is pretty easy to integrate. We've already done this before. We go 1/2 times u to the, this is 3/2 now. We bring that power out front and we flip it. And now we get a 2/3 instead. Okay? I mean, I can see you having trouble just, okay, what's 1/2 plus 1? And then that whole thing becomes like, oh my God, do I even understand math anymore? And I've been there and feel like your entire life is a lie. Yeah, I get it. So 2's cancel off here, and we're left with 1/3 u to the 3/2 evaluated from 1 to 9. Remember what this means. This evaluation bar means that we're about to use the fundamental theorem of calculus part 2. What is the fundamental theorem of calculus part 2? Well, it states that we're going to take this function, this antiderivative function that we got. We're going to plug in the upper bound in for u, and then we're going to subtract that same function, but now with the lower bound plugged in for u. So, here, of course, you would have a u and a u. Here, we're saying that u is going to be your upper bound, right? And so actually, I'll write that with a different color to make this more obvious. And then here, your u is going to be your lower bound. Okay? That's it. And so, we can do this quick here. What is 1/3 times 9 to the 3/2? Well, 9 to the 3/2, you could think of 9 to the 3rd power, but I wouldn't. I would think of what's the square root of 9? That's 3, right? That's that's just how you can think of that, right? This is power over root, and so you have a 9 to the root 2. That's a square root. So this becomes 3, and so it's 3 to the 3rd power, because that's the 3. That's the 3rd power, right? And that's 27. So this guy right here is 27. This guy's dividing it by 3, so this becomes 9. And we know that 1 to the any power is going to be 1, so this is just a 1/3. And so find common denominators here. This would be a 27 over 3, so you get 26 over 3. Okay? So really not all that much more work here. You end up with just converting your bounds, and that's really not all that bad. Yes, you have to use the fundamental theorem of calculus part 2, but again, that's just a bunch of algebra and also arithmetic. It's not it's not the end of the world. It's just more annoying work. It's more annoying than it is difficult. What is difficult is the stuff at the beginning to find that substitution. That's what I would consider the hardest part of this whole thing. That's what gives a lot of students that that I guess that's what gives u-subs a bad rap. That's I think a good way of putting it. So we'll do some more practice here. Let's do the integral from 1 to e of natural log of x over x dx. And so for this guy, what's our u going to be? Well, now this is probably your first time seeing this, but now we don't really have an inside function, do we? It doesn't really look like that, right? Yeah, our natural log has a normal x inside of it, and so it's fine. And so this is where you have to start thinking outside the box a little bit, okay? The u substitution might not be obvious for you. Remember how I was training you before to look for, when you make your u substitution, look for what it's going to cancel when you take the derivative. That's what you want to do. That's the foresight you want to have when you encounter a problem like this. That's why a lot of people have trouble with this exact problem, and that's why I brought it up in this video. When you have a problem like this, look, remember how the derivative of natural log of x is 1 over x, which would be, like if you had a 1 here, right? That's what this would be. That's exactly the substitution we're going to make here. We're going to call u natural log of x, and we're going to call du, well, that would be the derivative, right? That's 1 over x, and then you put the dx here. Now you have that substitution in place, right? You are going to be able to cancel some stuff off here. And so I'll plug that in here just to eliminate any confusion if you have some right now, and then we'll move on to the bounds. Natural log of x is now u, so this becomes a u. And then, well, this 1 over x, this wouldn't be an x dx, right? Because this x is in the denominator. So this entire thing is a 1 over x, right? You can even see that it's natural log of x times a 1 over x, right? That's what this thing is. Okay, you just got to take it apart. I know it's a little hard to see at first. But that 1 over x is going to become a du with the dx, and so you get that. Now, what are your bounds going to become? Great question. I'm glad you asked. This is going to be, well, x equals 1, so u is going to be the natural log of x, which is 1 here. And that's 0. Then you're going to go x equals e. U would then equal the natural log of e. And real quick, for those of you that don't know how to do this, let me just show you quick. Let's say that y equals the natural log of e. All right, how would I do this? Well, what we would say is, or actually, since that's basically what we have here with a u, I'm just going to write a u. Well, what we're going to do is realize that a natural log it's got a base of e, right? That's kind of implied when you write the ln. Or that is implied when you write the ln. It's not kind of. And so you get this, right? You have a base of e. And so what I like to do is use this circle trick here. I make this e bigger, then I make a little circle. I bring the e over here and the u over here. And so I make the e bigger, right? I'm going to put that over here now. And this guy is going to be to the power of u. Okay? It might make a little more sense if I wrap the circle the other way, right? The u comes around and it is now the power on this e. And then the e comes around and it is now over here. Okay? And so really what this is asking is e to what power is e? And you know that's 1. So u here is 1. So the natural log of e is 1. That's how you do that. Of course, I would just memorize that the natural log of e is 1. Or if you had a calculator, you would have solved that 5 minutes ago. So our new bounds are from 0 to 1. So I'll also write that in blue. And so now we just integrate here. If you take a reverse derivative of u, you're going to get 1 over 2u squared. This is now evaluated from 0 to 1, meaning that we need to use the fundamental theorem of calculus part 2 on it. So we're going to take this function, and we're going to plug in the upper bound and then the lower bound. So here goes a 1, here goes a 0. So as you can see here, this thing just becomes 1/2 because this is 1/2 and this is 0. Okay? Awesome. So moving on to this problem now what's going on with this u sub? Here's again where things start to get a little tricky. What is your u going to be here? There's no inside function, especially with trig. You're really not dealing with too many inside functions unless you're putting something like inside the trig function itself, like we saw in an earlier example. Here you really got to think, if I set my u as cosine, or if I set my u as sine, what is it going to cancel out? And here, if you set your u equal to cosine of x, right, you want to set it to the thing with the power, because, and if you have like a trig function that has like a power of 1, because watch what happens. If I do du here, we know that the derivative of cosine is negative sine. And that right there is going to cancel my numerator. And now I have a 1 over u squared. You see what I'm saying? So that's what I would do here. It's hard to see. It takes practice, guys. Takes practice. For me, I can say that right away because I've been doing these for a while, but I want you to understand that. And of course, we don't have a negative sine of x dx here. We just have a sine of x dx. So I'm going to divide over that negative 1. And this becomes a negative du is equal to sine of x dx. So making this substitution before we worry about any of our bounds here, we're going to get the integral of negative du, that's where the sine of x dx goes, and that's going to be over cosine squared of x. This is a cosine of x, that's u, so cosine squared x is u squared. Okay, and another way to write this would be negative 1 over u squared du. It's a little easier to look at it that way, in my opinion. So now we work on the bounds here. When x is 0, u is going to be cosine of 0, which is 1. When x is pi over 6 here, u is going to be the cosine of pi over 6. Cosine of pi over 6. Cosine of pi over 6 is cosine of 30. And so that is rad 3 over 2. So you're going to have an integral from 1 to rad 3 over 2. Okay? Awesome. So now we're going to integrate here. And I did say to remember this integral specifically, okay? Because we know that the derivative of 1 over x is negative 1 over x squared. And so the derivative of negative, or the integral of negative 1 over x squared is going to be 1 over x, right? That's the reverse derivative. And so this guy is going to become 1 over u, evaluated from 1 to the square root of 3 over 2. And now we use the fundamental theorem of calculus part 2, and yeah. So it's going to be 1 over, plug in the first bound, minus 1 over, plug in the second bound. First bound is rad 3 over 2. Second bound is 1. And so we get a 2 over rad 3 when we flip that first guy, and then this is minus 1. And yeah, guys, that right there is our answer. And so if you can see how this guy comes about, and this is the first time I've showed you something like this with trig, so I don't expect you to get this first try. Okay, but if you can see that whole substitution ahead of time, you are going to be really good at u-substitutions. Okay, it's going to be a breeze for you. And trust me, if you're taking Calc 2, you're going to be doing these all the time. Yeah, all the time. And so, yeah, that's a really good skill to learn. Okay, it's intuition in a way. It's just knowing what to do. But now we're going to move on to some weirder u-substitutions, and this is just something I've known. We have, I think, 3 examples left in this video, and then we're done. These are the problems I considered to be a little bit harder. I didn't really understand this at first. But here's the deal. We want to make a u-substitution here because we're not going to be evaluating this using reverse power rule. We can't do that here. So what would our u-substitution be? well, you'd see that, oh, this x plus 2 is our inside function here. And so you'd be like, let's make our u x plus 2. You don't have to erase that or anything. That's right. That is going to be our u substitution here. And when we take that derivative, we get dx. And so you might look at this and be like, well, what's the problem here? You were fine. We just made a simple u substitution. Well, look at this when you plug it in. You get the integral of, did this x go away? No, it didn't. So we're going to have to do some work there. And then you get an x times the square root of u. Right, that's what u was, and then we have this guy being du. So we are now mixing x's and u's, and it's like, what is going on? The solution here is actually pretty nice, though, and this is one of the nicer weird u-subs. All you have to do here is just realize that, if u equals x plus 2, then that means that x is equal to u minus 2. Just subtract that 2 over. And you know why that's nice? You're like, well, why this? How does this change anything? Now, instead of having a like you might look at this, you might be like, well, instead of having a rad x plus 2, now we have a u minus 2. How does that make anything different? Well, it actually does. This is something we can now use reverse power rule on, because what's inside the radical is now just a single variable. It's just u now. And well, that's u to the 1/2. We can distribute that through. Like right here, this is a u to the 1/2. So this is a u to the 1/2 times u minus 2 du, and that's much nicer than what we had before. So this becomes a u to the, this is a u to the first power, so when you multiply by this guy, you add the powers, and you get u to the 3/2. And then distribute it to the next guy, and you get u to the 1/2. Or 2u to the 1/2. I missed the 2. All right, so you get this guy. And so now just use reverse power rule. Here you're going to get a u to the 5/2. What? This comes out front, and it flips. So it's now a 2 over 5. This guy is going to be a 2 times something. That something is going to be this new power here. We add 1 to it, we get 3/2. It's going to be that new power flipped. So this becomes a 2 over 3. And then we add on our c. The last thing to do here, if you forgot, I swear to God, if you forgot this for this problem, I'm going to be mad. No, we're learning here, guys. U is x plus 2. We got to plug that in. So just plugging that in here, we're going to make this guy a 4 over 3. And then we add on the c. Bam. So it's just a little awkward to see that and be like, oh my God, I have an x's and u's, and that like is weird. And then you have to realize that, oh, you got to change this substitution. Now you got to realize that since u is equal to x plus 2, x is equal to u minus 2, you can plug that in. And so, that might not be too hard to see. When you mix something like this in with other problems, it can get a little weird. But especially when you have a problem like this. This is the same idea. You're going to have that same kind of weird u-sub. But now you have an x to the 5th here. Right? And so it's like, what? So what you're going to do here is you're still going to make the u that inside guy. You're going to make it that 1 plus x squared. We can't make the u anything else. And our du becomes 2x dx. But the problem is we don't have a 2x dx on the outside. We have an x to the 5th. And so what do? Well, we can write this guy as the integral of the square root of 1 plus x squared times an x times x to the 4th dx. Right, and by splitting that up, we now have that x as our substitution. We have the dx. Right, and actually to make that a little clear, just for your notes when you refer back to it. I'll do this as an x to the fourth and then an x. So you can see that x dx paired up right next to each other, right? And I'll do like little multiplication symbol there. So all we have to do now is realize that, oh, well, we don't have a 2x dx, we just have an x dx. And so we can divide by 2 on both sides, getting that du over 2 is equal to x dx. Right? And so this guy ends up being the integral of the square root of u times x to the fourth times, well, this is a du over 2 now, right? This guy becomes du over 2. And so, first off, we can get that 1/2 out of the integral, and then we have rad u, or actually, let me just already write it as u to the 1/2. But the problem is, what do we do about this x to the fourth? You see how it's like the same problem as last time? Just now it's like to a higher power. Well, we use our substitution again, right? We know that u is 1 plus x squared, and so we just now got to find a substitution for x to the fourth off of that. We can do that pretty quickly. If u is 1 plus x squared, we can just subtract 1 on both sides and get that u minus 1 is equal to x squared. Now, how do we get from x squared to x to the fourth? We're going to square both sides. And we get that x to the fourth is equal to a u minus 1 squared. And that's what we plug in. Again, that makes things a lot nicer because we can distribute this guy out. Okay, we can distribute that out, and we can distribute the u to the 1/2 through, and we get something really nice, or at least nicer than what we had. So this becomes 1/2 the integral of u to the 1/2 times, hopefully you can do this in your head, this is a u squared minus 2u plus 1 du. Okay, if you couldn't do that in your head, you should obviously be ashamed of yourself. That is terrible. I can't keep a straight face. No. So, anyways, this is a u to the 1/2 times u. That's going to be a u to the 5/2 because this is a u to the 4/2. And so you add the powers, right? This is a 4/2 plus 1/2 is 5/2. And then you have minus 2u to the 3/2. And then you get a plus u to the 1/2, right? Just distributing that u to the 1/2 through. And you get a du. Now, do quickly want to mention that, like, yeah, usually you see parentheses here. Actually, usually you don't. But I'm saying that you probably saw a lot of parentheses here when you started out with these integrals. You honestly don't end up seeing that like at all anymore, except maybe in textbooks. People usually just stop caring about that stuff because I guess we're lazy, or I don't know. So now we're gonna have 1/2 times. We do reverse power rule. This becomes a u to the 7/2. Bring that out front and flip it. This is a 2 times something u to the 5/2. Bring that out front and flip it. U to the 3/2, bring it out front and flip it. Plus c. Let's throw that 1/2 into the mix here. And we're going to get a 2's cancel here. So we get a 1 over 7 u to the 7/2 minus a 2/5 u to the 5/2 plus a 1 over 3 u to the 3/2 plus c. And then we're just going to plug back in here. We know that u is 1 plus x squared, so let's just make sure we do that here. Especially for one of these longer problems, it's very common to forget to plug back in. So plug back in. I'm running out of room here, of course, so let me just cheat. Go boop. There, you don't even notice. That's a joke. So this is 1 over 7 times a 1 plus x squared to the 7/2 minus 2/5 times 1 plus x squared to the 5/2 plus 1/3 times 1 plus x squared to the 3/2 plus c. Okay. And so, yeah, this looks pretty nasty as our final answer, but I mean, was it really that nasty? I'll leave that up to you. I think that honestly, this is kind of more the annoying part at the end. Like I said, the more difficult part is probably in the beginning there. Just trying to figure out what your u-substitution is, making all those different substitutions, all that weirdness, modifying your integrand a little bit so that you can make different substitutions. Like here, we split that x to the 5th up into an x to the 4th and an x. And sometimes you'll need to modify the integrand like that. This is the integrand, okay? Just like in this next example here. This is the last example for this video. This substitution you won't see right away, right? You just don't. You have to do something with this sine of 2x, okay? This integral is going to be weird if you don't. So what we can do here is we can rewrite this guy as the integral of 2 sine x cosine x. That's what sine of 2x is. And so that's why it's important to still know your trig identities, right? Just review them like, I don't know, once every couple days for like 5 minutes. And this guy is not sine squared, by the way. Remember, sine squared plus cosine squared is 1. So if we wanted this to be sine squared, it would have to be 1 minus cosine squared. But now you might see the substitution. I don't know. Do you see the substitution? What will we do here? Well, this is a little weird maybe, but if you do see that you can make, u equal to cosine x here, and then du would get rid of that sine of x, then yeah, that's exactly what happens here. Right? And of course here we don't have a negative sine of x, we just have a sine of x, so we're going to write this as negative du equals sine of x dx. Okay, and so this guy just becomes the integral of 2 times this guy, and this guy becomes the negative du, and the cosine x becomes u. So you get a 2u over, this is a 1 plus u squared now. Right, I think that might have thrown people off. They saw a cosine squared and they saw a cosine. That would have thrown me off too. I get it. It's like, I get it. With the cosine squared, just again, try to just think about it as like the base power. Think about it as cosine to the first power. If you call that u, yeah, you might end up with a u squared, but it's not that bad. Like a u squared is fine. A cosine of squared of a million x, whatever, dealing with something gross like that, that's not okay. So yeah, that's what this guy becomes. And then of course you have the negative du from the sine x dx. All right. So now here's the problem. You can write this, yes, as you can take out the negative and the 2 and write this as u over 1 plus u squared du. But can you use reverse power rule on this? No, you can't. So what you got to do is make another u-substitution. And that's a little weird. Sometimes you'll run into a problem like that. It's rare. It might not be something you get on a test. I couldn't tell you. But the substitution that we'll make here, we'll use a different variable. We'll call it w. This is now a w substitution video. W is going to be, what do you think? Well, we could make it that u squared, right? And then you see that the 2u du would go away, and we actually have the 2 out here. But look what happens if you do that. If you do that, you end up getting that you get the negative integral of, yes, this guy and the 2 are going to become dw. So I'll write that out here. But then this denominator becomes a 1 plus w. And that just doesn't work, right? That's not something we can use reverse power rule on. And so you got to be careful when you're making these substitutions, right? You always want to include the whole thing, especially with those constants, right? They can get you. You're going to want to make this u squared plus 1, right? Or 1 plus u squared, however you want to write it. Because then this, instead of becoming a 1 plus w, it's now just a w. And so this is something we can easily integrate, right? We know that the derivative, or the integral of 1 over w is going to be natural log absolute value of w. And now, the only weird part, I guess, is that we have two things to substitute back in. First, we know that w is u squared plus 1. And we also need to know that, oh, u is cosine of x. So this actually becomes the negative natural log of cosine squared of x plus 1 plus c. Okay? And yeah, that is basically going to do it for this video. U-substitutions are weird. I think we can all come to that conclusion after being through this video. But if you can start to see what's going on, you start to gain that foresight, that intuition as to what to do, this starts to become a little easier, and then it starts to become natural, and then you get it. Okay? So it's going to take a little more practice, and of course, for that extra practice, definitely check out that full Calc 1 course that I have linked in the description down below. And yeah, so that's going to do it for me, guys. I'll see you soon.